Alright, so now let's proceed to the other example for Tbat. So the next question is 0.9 kilogram of hydrogen gas is cooled from 400 degrees Celsius to 350 degrees Celsius in an isometric, which is isochoric process. How much heat is removed from the system? So here, the substance is hydrogen gas. So for this question, we are going to use the equation to solve these problems. And then next, we're going to extract all the informations given. So this is the mass, and this is the temperature, ST1, and this is the temperature, ST2. So mass equal to 0.9 kilogram. Temperature ST1 is 400 degrees Celsius, which is equal to 673.5 Kelvin. T2 is 350 degrees Celsius and equal to 623.5 Kelvin. And this is isochoric process. So isochoric process, V1 is equal to V2 equal to V. So how much heat is removed from the system? If we look into the non-flow energy equation, Q minus W equal to delta U. So we know that for the work will be P dV, and then we know that the volume is the same, so the changes between the volume will give us 0, thus the work equal to 0. What's left for our energy equation is Q equal to changes in internal energy, which equals to CV, specific heat at constant volume, times with the difference between temperature at state 2 and state 1. So again, this question requires us to give the answer in the unit of kilojoule, thus we are going to multiply with the mass. So Q equal to the mass is 0.9, and the specific heat at constant volume for hydrogen is not being given from the question. So we look into the property tables, table E2, and then we look for hydrogen. So this will be the hydrogen, and the specific heat at constant volume will be 10.183 kilojoule over kilogram Kelvin. .183, and then times with the difference between T2, 623.5 minus 673.15. So you're going to get the answer for the heat transfer is minus 458.235 kilojoule. So the terms negative over there is representing the heat that is being removed from the system. All right, so next question is 4 kilomole of air initially at 1 atm and 295 Kelvin are compressed isothermally to 8 atm. How much heat is removed from the system during the compression? So the substance is air. Again, we're going to use formula or equation for the ideal gas. And then given here is the number of moles, N, which is 4 kilomole. And then given over there is the initial condition, which is P1, 1 atm. And 1 atm is equivalent with 101.325 kilopascal. And then we have also the temperature, ST1, which is 295 Kelvin. And then we know that this is isothermal process. T2 is equal to T1 equal to 295 Kelvin. And then we have P2 equal to 8 atm. So if you convert into kilopascal, you're going to get approximately around 810.6 kilopascal. So how much heat is being removed from the system for isothermal process? For the ideal gas, from the non-flow energy equation, Q minus W equal to changes in the internal energy. So we know that for the internal energy is given by CV T2 minus T1. Since the temperature is the same, it will give us 0 for the difference between the temperatures. So what's left is Q minus W equal to 0, thus the heat transferred will be equal to the work for this particular isothermal process. So the work is given by P1 V1 on P2 over V1. Okay, so we are going to find the value for the volume at both states. The first one, we're going to look into the volume at state 1. We're going to find the V1 by using the equation, ideal gas equation. P1 V1 equal to mRT1. So we're going to find the volume 1 over here. Okay, so we have the value for P1. We have the value for T1. Right? So for the specific gas constant R for the air, you can find it by referring to the property tables. Okay. So as you can see, for the air, the gas constant is 0.2870 kilojoule over kilogram Kelvin. Alright, so next for the mass is not being given by this question. We can determine the mass based from the equation of mass equal to molar mass times with the number of moles. So we do have the number of moles, and if you refer to table 1 for substance air, you can find the molar mass is 28.97 kilogram over kilomole. So the mass will be equal to the molar mass times with the number of moles, and you're going to get the value of 115.88 kilogram. So now we do have all the data necessary for us to determine volume 1. So you're going to get the value for volume 1 is equal to 96.8268 meter cube, right? Since we know that this process occur in constant temperature manners, so then we can use the relationship P1V1 equal to P2V2. So you can find the volume 2 over here. And then V2 is equal to 12.1034 meter cube. Now we have the value for P1. If we look into this equation to find the work, so we have the value for P1, we have the value for V1 and also V2. Right? So if we substitute and calculate, we are going to get the value for the heat transfer going out from our system is 20,401.3095 kilojoule. All right, so now Let's have a look into the last question. For the Tbat example, in an isentropic compression of an ideal gas, P1 is equal to 100 kilopascal, P2 is 200 kilopascal, V1 is 10 meter cube, and K is 1.4. Find the V2. So when you found the terms isentropic, it also brings the meaning of the process will be inadiabatic. So we are going to use similar to polytropic, but the polytropic index will be replaced with the K or gamma, P1, V1, and then the polytropic index will be equal to gamma, which is power of 1.4 over here, equal to P2, P2 power of 1.4, right? So we do have the pressure at state 1, pressure at state 2, we have the volume for state 1, and also we get the ideals of ideal gas, then we're going to use the equation. Thus, from this relation, we can find the volume at state 2. Okay, so then you're going to get the answer 6.0951 meter cube. Right, so that's it for chapter 2. I hope you guys really understand so far our discussion. If you found any difficulties, please do consult with me. Good luck, everyone.